Number 30. What force is needed to pull one microscope slide over another at a speed of 1 centimeter per second if there is a 0.5 millimeter thick layer of 20 degrees Celsius water between them and the contact area is 8 squared centimeters? All right. So here's a little diagram, right? We have two slides, one's in red, one's in black. Here, the surface area, I just assumed, right? It's going to be basically just the surface area of one of them moving. So here it is, 8 centimeters squared. It's moving with a certain velocity, has a certain thickness, right? Here's the viscosity of water. We developed this formula in the prior problem, all right? So we just have the force will be equal to then the viscosity of the fluid multiplied by the area of contact between the two surfaces multiplied by the velocity of the moving object divided then by the thickness of that particular fluid. All right, so basically we have all we need, right? So we can just throw everything on into this formula. All right, though this should, if you think about it, this formula should make sense. If you're just thinking about, these two surfaces, moving in relation to one another, it doesn't matter if you move the bottom one to the left or the top one to the right, it would have the same effect. If you though notice, right, we have the area of whatever surface area is in contact. The larger this is, the larger the force becomes. The larger the retarding force is. This is the retarding force, so the force that opposes the motion. That makes sense, right? The larger this area is, it would make sense that there's more friction, okay? The higher the velocity is, that also makes sense that the more friction there is. And also, this is inversely related to then the thickness, okay? Meaning that as this thickness becomes larger, right, what happens to the force? It's lower. And that kind of makes sense if you start to think about it, right? So all we need to do now, so hopefully these variables do make sense in terms of their organization. Now, we have the viscosity of the water, so this is 1.002 times 10 to the minus 3. The area of contact is going to be 8 squared centimeters, but we need to do this conversion, right? So simply take that, multiply it by meter over centimeter, 100 centimeters in a meter, and then square that, okay? And that's what you're going to be multiplying. So it's really 8 divided by 100 squared in here for the surface area. The velocity was in centimeters per second. Again, we got to convert this thing into meters. So just take this and divide it by 100. So we have 1 over 100 here. Then divide it now by the thickness. Oh, look, it's in millimeters. Wonderful. We got to convert that, right? Divide this baby by 1,000. So it's going to be 0.5 over 1,000 now. And we could just plug it all in. All right. So let's do that. So we have basically 1.002 times 10 to the minus 3 times 8 divided then by 10 to the 100 to the third. I just combine those hundreds in the numerator there, and then divide that all by now in parentheses 0.5 divided by 1,000, and here we go. So we have 1.60, right? 3 sig figs, I guess, or whatever. Maybe 2 because of the temperature. Doesn't really matter. But then again, the temperature gave us the viscosity, so I guess, and that has force. So I guess we should do the limiting value of 3. Who cares? So 1.60 times 10 to the minus 5, and this is in terms of newtons. All right. So here we go. There's the force value. And that's it. That's the retarding force, okay? Force that will oppose the motion. Guys, thank you so much for tuning in. Appreciate it very much. Please remember to subscribe. See you next time.